Welcome, everybody. My name is Melissa Hanson, and I'm the Vice President of Product Marketing for Nexa 3D, as well as the host for today's webinar. So the response to this live event, and frankly, the newest member of our Nexa 3D lineup of printers, the XiP, has been overwhelmingly positive. So it's great to see so many of you here today and counting, and from around the world. So thank you for spending this time with us to learn a little bit more about the XiP, the technology that underpins its features and capabilities, as well as the broader ecosystem and the workflow that uniquely enables it. Before I turn it over to Michael, our main presenter, on all of that today, I'd like to cover just a quick orientation of our Zoom tools available to you for interaction. Many of you may be familiar with it, but you should see in your Zoom toolbar at the bottom of your screen a chat feature. I see some of you chatting away already, which is great. You're welcome to use that for comments and questions for the broader audience, really for everybody to see. But when it comes to submitting a specific question you have for me and Mike along the way about the XiP or the content, please use the Q&A feature that you should also see at the bottom right of your tool set. You won't be able to see the entire list of questions submitted along the way by everybody, but Mike and I will, and we are going to do our very best to answer as many of those as possible following the presentation today. So we'll get to those at the end. So with that, I'm happy to introduce you to today's main presenter and my colleague, Michael Currie. Michael is the General Manager of Nexa 3D's Desktop Business Unit, and he joins us today from our headquarters in Ventura, California. He is what we say an engineer turned business person. So to that, he will euphemistically say often that he turned to the dark side. But in all seriousness, he loves working in tech companies. He's got a lot of experience with tech, whether it be IT companies, marketing technology companies like HubSpot, robotics, or even 3D printing companies. So he brings a problem-solving first approach and a lot of empathy and understanding for the customer, really having been one himself previously. So Michael joined Nexa 3D just about 6 months ago, really to bring the XiP to all of you, and along with all the post-processing gear that surrounds the printer at the desktop. With XiP, you'll hear a lot about this today. Our focus is really on the act of 3D printing as an individual user, and even up to teams of users with mixed experience levels. So whether you are a beginner user or an expert user, our goal is really to make that experience quick, easy, safe, and economical, and importantly, all the while enabling a really high level of print quality to achieve your specific design and product objectives. So without further ado, here's the man who is about to share just how XiP delivers all of that for you. Michael, take it away.
All right, thank you very much. Welcome everybody, and thanks for joining again. Melissa, thank you for the gracious introduction. It's always hard to talk about oneself, so I'm glad you talked about me for me. And I want to jump into this, but before I jump into with the XiP, I also want to introduce you to Nexa 3D. So we are a younger 3D printing company, and so I would kind of want to address why we are here and why we exist. And so first off, there are many 3D printing companies out there. There's many manufacturing companies and also many design companies. And Nexa 3D was started as a 3D printing company that places sustainability at its core. So in honor of Earth Day last week, we're all in the endeavor of creating and adding things to our planet as designers and manufacturers. So until we colonize another planet or Mars or somewhere else, we need to be in balance with our planet. And so the responsibility is on us as makers to bring the best products that we can to delight, that perform very well and last and stand the test of time in a way that's very energy and resource efficient. So that's why we've come into being. And what does that mean? Well, we have what we call a massive transformative purpose at Nexa 3D. and that's to digitize supply chain sustainably. And this is one of our overarching aim and the ethos of what we're doing. So this kind of cuts two ways. It means that we want to bring you the best tools and the best processes to allow you to digitize and you to become sustainable yourself. And then internally, we're also walking the talk and making sure that our internal supply chains, our internal company culture, and how we design and build and market and sell our products is also sustainable. So I guess there's a joke, if you go to one of our Nexa booths at a trade show, you'll see QR codes everywhere. And that's by design. We're trying to minimize the amount of paper that's in the world that might get thrown out after a few days from when returning back from a conference. So we really live and breathe it, and that's a motivational backdrop, and that's kind of what got us into the idea of the XiP. You probably have seen a slide like this before, and it shows sort of the arc of a product over its product life cycle. So you have on the vertical axis the number of parts that are being used over a period of time, and this is sort of the life cycle that 3D printing is trying to transform. There's obviously these two hallmarks, these two gates where you go from product development, ramping up into a mass production, and then once your product is now obsolete or there's a new model available, then you go into a down phase where you're achieving end of life. So this is where Nexa 3D started tackling probably one of the hardest challenges to digitize supply chain sustainably. We wanted to make the biggest dent we could. And to make the biggest dent, we said, okay, let's go straight and put ourselves in this middle area where we're talking about mass production and bringing additive technologies to bear on mass production. Not an easy task. It requires very high part quality, consistency and repeatability from within the actual printer itself and also within your fleet of printers. And most importantly, to achieve mass production, you need throughput, great throughput and great cost. So this is where Nexa 3D started, and this is where our first product line exists, and that's where we're cutting our teeth. And when you step back, and there's a lot of great surveying that gets done by people like 3D Hubs, et cetera, and they ask, well, what do you use your printer for? And while Nexa 3D started as end-use parts, production parts, there's still a large number of people who are doing prototyping. So prototyping is almost half the pie here. And you have people doing jigs and fixtures, which I would basically consider prototyping production itself, almost another quarter. So you have a large number of people who are doing other things other than this mass production area where we started. Asking another question, how big are your actual production part runs? Overwhelmingly, 2/3 of the people are making 1 to 10 parts. So there's this other area of the product life cycle where there's another product out there that we think is appropriate. So with that in mind, there was a hint there that there might be something that we should be looking into. So we investigated it, and we found that there are some definite gaps in the desktop 3D printing world that we hoped or we think we can address. First off, most people at the desktop level, their printers can print 1 or 2 prints per day. Maybe they might have an overnight build. But there was this gap where you have hourly or even sub-hourly prints where you could do 5 or more design generations in a day. So that's one gap we saw. The next was most desktop printers, printers meaning the people, not the printers themselves, I should say users, they might have 1 or 2 printers. And so there's not a lot of redundancy in the office environment or in the desktop environment. So having a reliable printer is really important at the desktop, because if you don't have your printer or it's not working, that means you have basically zero capacity. In a mass production world, you usually have enough redundancy where that is not an aspect. So here it's almost binary. You're either up and running or you're not running. Thirdly, a lot of desktop companies are moving from desktop into the industrial space, and they're kind of moving up the chain. And so we actually wanted to flip this over and say, can we move down the chain? And what that provides you for is the scalable workflow idea, where you can, if you're at the desktop, you know that you can scale your workflow into a production machine if you need to. And doing so, you're keeping the same set of materials, you're keeping the same set of processes. So it's a very seamless transition. And then the last one is material choice. So I think Amazon and the Netflix of the world have really spoiled society with choice. And that's no different than in 3D printing, where you have a lot of major chemical manufacturers who are proliferating in the space and bringing a lot of new materials to bear and solving a lot of the problems that typically had come up. I always hear from new 3D printing users, aren't your parts brittle? Well, that was something that what you could say back a decade or so ago, but more recently, these manufacturers are coming in, solving those material issues, and why not take advantage of them? So with that, we created the XiP. So first off, meet XiP. XiP is an ultrafast desktop resin 3D printer. And this is showing off the XiP on a desktop scale. So that's give you an idea of what it looks like, just kind of whet your appetite, and then we can get into some more specifics. So then completing the picture here, if you add XiPs to this life cycle, you can basically see you have your desktop machines feeding your industrial machines, feeding your desktop machines, and sort of this endless cycle of being able to move seamlessly up and down your number of parts you're creating with a process you're using. So that was where we were going with this product line. And the rest of this conversation, I'm going to dig a bit into vat polymerization, which is the class of technology that the XiP falls under, how the XiP is different, and also show you what the workflow looks like and some parts that have come off that. And at the end of the presentation, open it up for Q&A. I'm sure people have a lot of questions, and I'm really excited to answer them, and I'll stay as long as it takes and answer as many as I can. All right. So up front, I'll give you a quick set the stage with the specs of the XiP. And so the XiP is roughly 190 by 120 by 210 millimeters, which is a 4.9 liter build volume. Layer heights vary by resin, but very, our standard resins have 50, 100, and 200 microns, and I'll talk more about what layer height is later. And uniquely to our technology, we're using an LCD, which is like one of the core aspects of our light engine, which we'll talk about. And our resins come in a cartridge system. I'll show you that. And more importantly, I wanted to make sure I get it out there up front. You're probably wondering, how much does this cost? The XiP retails at $5,999 in the US and Canada, and a full system, which has services, post-processing, and all of our other gear would be just under $8,000 at $7,999. All right, so jumping in. So this XiP falls under the class of 3D printing called vat polymerization. And as opposed to FDM or SLS technologies, it involves taking a liquid resin, applying light of a certain wavelength to it to create a photo curing reaction, which then hardens it into a plastic. And there are a few different generations of this technology. The first generation, which is called stereolithography, was the initial 3D printing technology invented by Chuck Hull and then further developed by 3D Systems in the 1980s and 90s. And then the second generation was the idea of digital light processing. This is a idea invented by Texas Instruments and then brought to 3D printing by EnvisionTEC in the late 2000s and early 2010s. And then the third generation, which we're on now, which I'll talk a lot about, which all of our technologies in X3D are a part of, is what we call masked stereolithography, or mSLA. It can be a little bit of a mouthful, so I'll try to use just mSLA going forward. If I try to say those two words, I'll get tongue-tied. And this was brought out in the mid-2010s by Photocentric. And our version of that, our secret sauce, if you will, is what we call the lubricant sublayer photo curing technology. So we'll get into those and the trade-offs and some of the improvements in this conversation. Okay, so just to set the stage, this is a version of stereolithography, which is in the inverted format, and this was popularized. So desktop vat polymerization in this inverted fashion was popularized on the desktop by Formlabs in the 2010s and really created this marketplace. And what you have here is you have a laser source that is then bouncing off of a mirror. Sometimes it's two mirrors, and then that laser source is basically painting out or rastering out where the curing reaction should take place. and to create your part. So as each layer is cured, then the z-axis will move up by a discrete amount, typically in the 50 to 200 micron range. And then the process repeats itself. So your CAD file that you sent to your slicing software creates all the instructions to drive the laser around, and then the printer works in conjunction with that design to then effectuate your part. So great. This is the advantages here. This is a well tried and true method. Everyone knows about it. There's ample light from a laser source for curing, and this gives high levels of surface finish and detail. So this is really the reason why people are using that photopolymerization versus, say, FDM or SLS, because of that great surface finish that you inherently get. The disadvantage of this system, because we're at a desktop, we don't have a lot of space. So that what you call the throw angle or the projected angle means that if you're further off axis, your actual laser spot size will change. So dead on, it might look like a circle. Off axis, it might become more ovoid. And that's an area where that's one disadvantage. Second one is you have a reliability and maintenance issue. So as I'll show in later generations, solid state has kind of entered the game in 3D printing to get rid of some of these areas where maintenance and reliability can be an issue. The second one is the digital light processing process. So this little chip, instead of having a mirror, you basically shine a lamp source onto a small chip. Now this chip has millions of tiny small mirrors, called a digital light projection chip. And this is what you have seen in projectors for home studio, home theaters. And this came into light. And the difference here is because you're using a lamp and shining the lamp onto these mirrors, you can mask whether you want to bounce that light towards the resin or not. So you can basically choose to cure or not cure. And if you basically create your layer on all the mirrors, you can create a full layer of curing. So this dramatically increases the speed of 3D printing. Secondly, there's a set of optics that you can choose to either make those pixels shine on a very small area. So if you want to be a jeweler and you want to have very fine detail, you can put all those pixels in one spot. Or if you want to print quickly over a large scale, you can spread those pixels out and put them over a larger build area. The trade-off there, obviously, is that, again, you have a projected angle issue, whereas you're off axis, your pixel size will start to change because you're in a focal system. And in the desktop world, you don't have a lot of height to work with, so your focal lengths are typically shorter than they would be in an industrial system. Lastly, the disadvantage here, you don't really see a lot of 4K DLP systems out there at the desktop. If you're in the market for home theater, 4K and larger systems are getting very expensive, and that's also the case here for 3D printers. And so that's one disadvantage of this approach. Okay, and so this last third generation, what we're doing here is basically each one of these generations really just changes the light source, if you will, out. And there's some other technology too we'll talk about, but the light source is the primary one that separates the generations. So third generation, what we're doing here is we're taking, instead of a lamp and instead of a DLP chip, you're starting off with an array of LEDs or an array of discrete light sources. And then you use a passive set of optics that then collimates that light. So imagine you have a flood lamp or a floodlight of collimated light, and then you put a masking layer before the vat where the resin is, and this is usually done with an LCD. So the LCD is, you're familiar with that from iPhone, iPad, laptop technology. It allows you to basically address pixels on or off, and then whether it's on or off, it lets light through. And so that's how this process is done. And the great thing about this is you're still curing a full layer at a time, but the great thing here is there's no projected angle issue here. So across your whole build volume, each pixel is going to define basically a perfect pixel. Not only that, because usually the LCD is stuck right below the vat where the resin is, you're getting what I would call like pixel sharpness, meaning you're masking the light at the last very moment before it starts curing. and that's going to improve your precision, ability to kind of create that precise pixel. And this technology is riding what I would call the piece dividends of the iPad wars and the iPhone wars and the tablet wars. So this technology is readily available, and it's also very inexpensive. The downside of this technology is, and these are all being worked on, the LCD itself is now a consumable. Before, the other systems had very basically permanent optics or permanent long-lasting light sources. This LCD layer needs to be replaced, and I'll talk about later how we address that. And because you're using discrete light sources now, you need to do a lot to calibrate and make the photon or the power field very level. Otherwise, your system will be set by what I call like your weakest photon or your weakest light source area, because that's going to set your timing of your process. And that's the 3 generations. So the XiP is in that 3rd generation. The other really big technology that I want to talk about, because it's very important for Nexa 3D, is the idea of peel forces. So if you're, let's say in this analogy, you're 3D printing a loaf of bread. In the case here where you've just cured one slice of your bread here, in this analogy, it's basically existing between a substrate and this interface and then your build plate. And so for a very momentary point of time, you basically filled the gap between your build plate and your substrate with your cured layer. And so now there's the idea of the peel. How do you separate this and get ready for that next layer? Because you're going to be lifting this up by 1 layer height. And that's what we call the peel. And if you look at that interface very closely, what you're really seeing is that you have a cured layer, and then you have a substrate, and then you have in between what we call intermolecular forces. This is not a bonding, like a chemical bond or an ionic bond. It's weak interactions between these 2 layers. And so you have to overcome that to move the part. But this has to be a very careful process, because if you exert too much force on it, you could literally rip the part out of its proper position. So there's a few different ways to do that. One idea is having a rigid substrate, where you have a rigid substrate and then you have an interface layer on top of that. Here, the idea is you have 2 options. You have to either break all those bonds all at once, and that takes a lot of force. Imagine if you're trying to pick your hand up off of a piece of duct tape that you've stuck it to, it's very difficult. Or you have to shear your hand away, or shear the surface away. The challenge there is that you have to have very stiff, strong materials to be able to handle that force, or you have to design your part in a way that has beefier walls, thicker cross sections to be able to handle that. The next version is a flexible substrate. And then this is in the class of a low separation force. And here your strategy is you want to peel the membrane away. And this gives you a very low force. Of course, you can't just have a floppy membrane or a floppy substrate all the time, because then you never would be able to form your layers. So temporarily in this system, you need to have some rigid surface to form your layer against. And then the last one is what I call a cure-free interface. And here you have basically a dead zone between the cured resin and the film. So for instance, Carbon 3D has this oxygenated layer where it's makes it very difficult for the part to cure. So there is no intermolecular forces, and there is no peel force. So that's the other option. It's a very delicate process, and it also relies upon the ability to reflow resin and back into that area as you start lifting that part. So there's pros and cons with each of these methods, and I just want to give you that backdrop. And I'll come back to that the graphic in a second. So our technology we call LSPc, lubricant sublayer photo curing technology. It's basically our light stack. So we have a stack of LEDs and lenses. We have our LCD mask, in this case a 4K mask. And then we have our membrane or our film technology. And this is a proprietary technology for us. It has extremely low peel forces and allows us to separate those layers extremely quickly so that we can have a very rapid print process. It also imparts a very low force on those layers so that they stay in place, so we can take advantage of that 4K resolution we're getting. In terms of just timing, every print, every build timing is a little bit different. But on average, we're seeing if you're taking 1 unit of time to print something on the XiP, you might take 2 or 3 units of time to print something like that on a DLP system, and 5 to 7 units of time to print the similar thing on a generation 1 SLA machine. So we're really getting a lot of speed here, and I'll try to prove that to you later in the talk. And then jumping in back to that former diagram, I showed you this idea of peel forcing. And so what our membrane does is, because it is lubricated, it doesn't like to stick to the substrate below the membrane, nor does it like to stick to the part. So it's kind of non-stick surface. And what that allows you to do is lift or free itself from the substrate and be able to engage in this peeling, this tape-like peeling effect. And so as it lifts higher and higher, you can start to see at the edges of this part, you'll get this tape peeling effect. This is happening obviously in 1 dimension in this diagram, but it's actually happening in 2 dimensions on your actual parts themselves. And the idea here is that it's much easier to break one of these bonds at a time by having this stretchy layer. And as a result, we have the Everlast 2 membrane, which is the core of this. This is the membrane technology that underpins the LSPc technology. And one, it's very flexible. It's very durable, and more importantly, it's also inert. So it's not going to participate in a lot of those intermolecular forces that we talked about earlier. It's lasted over 50,000 layers, and it doesn't cloud. It's optical grade, and it is a great fit for us. And this is what drives our process. Okay, so the geometry of the XiP, I want to give you some idea of the geometry here. We're talking about a 4.8 liter build volume. Again, in this analogy of the bread here, 1 slice in the XZ dimension would be 50 to 200 microns based on your resin settings. And then in the XY dimension, you have this grid of pixels. And so this is a 4K screen. So the smallest pixel is 52 microns on the side. So it's approximately the width of a human hair. So we're able to have pixels the size of a human hair. One of the earlier concerns with this idea of digitizing 3D printing was you have this idea of a pixelated or a pixelized image. And it was a concern, and I think it was addressed in a few different ways. So what we learned is that you can actually do a grayscaling effect around your edges. And this is done with an LCD. It's done by basically telling the LCD to kind of partially block the light and use the different grayscale tones they have. Or in the DLP sense, it's used by pulse width modulating your laser light and basically basically having a duty cycle of how long the light is actually shining at the layer. And this gives you the ability to create sub-pixel resolution. I love this picture from an early Autodesk Ember research study where they basically had a tower and they wanted to create a 30 layer by 1 pixel wide angle to it. And they were able to take these different grayscale values and synthetically create this 3-degree angle across that side of that wall. And what that shows is that you can use this technique to get, first off, sub-pixel resolution, but then also to digitally create extra surface finish that you wouldn't think would be there if you thought you're working in a binary realm. So when you look at something like a Deadpool here, this little, I don't know if it's a grenade or a water bottle he's carrying, probably a grenade knowing Deadpool. This has a lot of XY curvature, so it should have this pixelation if it were not for the anti-aliasing, which that's what they call the technique and that grayscaling technique. So even though we're in a pixel regime, we're still able to get really great sub-pixel resolution and great surface finish. So that is one of the hallmarks of the mSLA technology. Okay, industrial grade. We took the approach of starting with industrial components, making this an extremely robust system. And what we have here is you have a sheet metal underbody, and then you have a solid machined aluminum center body on which the LCD lays and sits. And with that, you have a high performance ball screw that is creating the Z-axis. So you want this structure to be as rigid as possible. You know, if you're starting to talk about pixels that are the size of the human hair, you need the entire system to honor that level of resolution and keep things in alignment at that level to get that very precise printing. So in our system, you know, we've removed the mirroring systems, we've removed some of the solid state mirrors, and now the entire light engine is almost passive. The only thing that's moving is electrons, basically, and photons. And the only true moving part is the Z-axis, which we put a lot of emphasis into. With that, we then enclose the zip in like almost a exoskeleton or roll cage, if you will, of a billet aluminum. And then we also pin the Z-axis into the top frame. So you're creating a very well-defined unit, which is perfectly aligned and will stay in alignment. On the desktop level, you see a lot of what we call cantilevered Z-axes, where the Z-axis will be freestanding. And a lot of care needs to be taken to make sure that that Z-axis doesn't wobble or wiggle. As you are peeling away from a part, Newton's third law, it will pull on the actual build plate, and we'll see some dancing, if you will, in some machines that don't have a really good anchoring for the Z-axis. So that was what was very important to us. This, we believe, is going to give the zip a long life and also a high level of accuracy and detail. All right, and on to materials. I know this is we asked people to submit questions in advance, and this was a big topic area that came up. So I want to tell you how we approach materials from the zip perspective. So we have basically, we're not a closed versus an open system. What I would call we're a both here, and so I'll tell you what that means. So we will have branded or validated library of resins, and we at the moment don't have our own material scientists. We partner with folks like BASF, Keyprint, Loctite, and Additive to give us great materials. And then what we do is we certify those on the zip. We perfect the print processes on the zip. We also put the parts through the zip desktop post-processing workflow, and then send those parts back to the chemical manufacturer. And then they measure the results, they measure the functional properties, and then they give us the thumbs up or thumbs down if it works. If it works, then we put it in the portfolio and we bring it to you to use on the zip. Now, I mentioned earlier that material choice was a big thing. So outside of the materials that we can bring, there are a large number of other materials that are suitable for DLP printers and other mSLA printers, which probably have a very good shot of printing on the zip. So for that, we have an open material platform, and it's basically a license unlock to access the same settings that we use internally at Nexa 3D to create our own print settings. So that's how we're going to handle this. And as we get going, we'll start to work with the community and see what resins the community is having a lot of success with. We'll do a lot of communication and sharing, and we hope that we can build this almost this pyramid of taxonomy, if you will, of materials out there. Where you have, the branded ones at the top of the pyramid. You have this middle layer of community-sponsored, community-certified materials, and then you have the rest of the field where are future resins to be explored. Out of the gate, we currently have 6 resins ready to go, and you can order them now with your printer. And I won't talk through all of them here, but the slides will come out in a subsequent email to everyone. We have a number of other ones that are in the process now of being validated. So within a few weeks of launch, I'm expecting to have 10 or more. And then this number should just continue to grow as we put out more zips out in the world, and we have more time between now and then. Particularly on dental, I know that there are a lot of dental people on here, so I wanted to spend a little bit more time on dental resins and how we're doing there. So currently on the zip, we're partnering with Keystone. We also are partnering with BASF on some other materials on our industrial machine. And so our approach is we're going to validate the most common dental applications for the zip. And then if you want to get ahead of us and get ahead of Nexa 3D and do some other indications or other applications, then I would recommend you look at the open material platform and go down that route. And in the pipeline right now, we have a model material ready to go, and we are in the progress of validating with our material partner a surgical guide material as well as a soft splint material. And then if you're wondering, okay, well, how fast is this print or how accurate is it? We're able to produce 7 horizontal arches in 29 minutes on the ZiP. And from an accuracy perspective, showing 90% accuracy within 100 microns for a model across the entire surface of a full arch, and 80% or greater for a quad model with a die. So those are all within the clinical required accuracy for those applications. I'm really excited about that. Okay, so the workflow. We have a few things here. We're going to prepare our CAD model for printing. Obviously, we're going to print that model. Then we're going to wash, cure, and finish. So I'll take you through all of those steps in an abbreviated fashion and also show a video of how that looks on the ZiP. And first, I will take you through, this is not my video, there's a speaker on this video, a little bit of an orientation to our Nexa X print preparation software.
Nexa 3D proudly announces Nexa 2.0, an intelligent file preparation and printer management software to get from part to print in minutes at production scales. Nexa 2.0's intuitive controls enable effortless pre-print setup of even the most complex jobs. Robust support structures ensure the consistent quality and accuracy of parts. Our software's state-of-the-art slicer analyzes and optimizes each unique build to ensure the high success rates and accurately estimate print times. Finally, Nexa X 2.0 is accelerating productivity with the built-in intelligent printer management system that is designed to unlock the full potential of your printer fleet.
Okay, thank you for taking the time to watch that. I got a chance to get some water and power through the back half of this presentation. So he mentioned Nexa X 2.0, we're now a little bit further, we're at 2.4. And for the ZiP, there's going to be 2 versions I mentioned. One is a basic version, which comes free with the ZiP. And this gives you all of the factory print settings to print with our branded or our labeled resins, plus a few extra knobs that'll give you some chance to change some exposure schemes within some confines or some bounds to not go too far one way or the other. What I would say here, the 2 areas that I really would call out are our advanced support generation. We create our supports through our partnership with a company called Paramatters. And this is really giving you a lot of extra knobs to dial in your supports to help you execute on what would be very difficult prints to do and make sure that they come out proper. Also within this, there's an idea of a tabbed application window, much like your Chrome browser, where you can be working in multiple instances of Nexa X at the same time. On the professional side, this is a license unlock, and the big item here is unlocking all of our custom resin settings. So I'm listing out a few of the things you can control, but this is basically the same set of controls that we use to develop all of our internal print settings at the company itself. So we really think that with this dual version, we can help folks who are new or learning 3D printing stay in good swimming lanes to make sure they get good prints, but then also give power users and people that want to get ahead of Nexa 3D and get to other resins that we've not gotten to yet, the ability to go do that. So that's how we're doing that with our software. Okay, so the VAT system, very similar to desktop systems. We have a removable VAT system. The idea here is that if you want to quickly change out your material, you can remove the VAT, which has material in it, put it on the shelf and put a new VAT in. The benefit here, or I guess the difference here, is we decoupled the vat frame and the membrane itself. So if your membrane wears out, you can just simply replace the membrane film and keep the vat. So the vat now becomes basically part of the machine forever. And we'll show you a bit more on that in a bit. And then the vat system itself, it all is magnetically aligned. So we have a set of magnets which align the LED, which is aligned to the lenses, which is aligned to the LCD, which then is aligned ultimately to your vat. So you get this very good alignment across the whole light engine. And then we have a very simple gravity feed system where you put your cartridge in, and it, like almost like a bird feeder, will fill up your vat and maintain a maximum level up until the point where there's literally no resin left in your cartridge, at which point the level will start to fall as you print more, but we'll keep you in good stead by giving you warnings and indications about needing more resin. Okay, so I want to show you a short demo. This is a demo where we're printing a three-way hose connector. There are 30 of these on the build plate. They're about 32 millimeters high, and we're printing in a fast draft material from BASF. And we're showing this print, how it could be printed in 13 minutes. And if you were to time this out on another typical Gen 1 SLA machine, this would be 2 hours and 45 minutes. So this is just an example, but it shows you how much quicker you can achieve your parts with this technology. So here I go. All right, I'm the only voiceover for this one, so I apologize. So this is the XiP, has a nice internal lighting scheme. Now this is showing how to replace the membrane on the vat. So there are these quick latches, almost like Tupperware-like latches that hold the four sides together. And once you have them in place, it's just a matter of snapping down on each side. On the top side of the vat, we have a spout, which we call it, which mates with the resin in the system. And now the user is going to insert the vat assembly, and you see those magnetic attachment points. Once it gets close, the magnet will basically suck the vat into perfect alignment. Bottle on the back is an NFC tag. This is used to correlate the bottle to the vat and the file, and this is able to be used both for the branded resins as well as the custom resins. So you can basically write to those cards. We designed the gravity feed system to feed out in less than 5 minutes for all of our resins, so you can get printing very quickly. Now installing the build plate. The user's clicking a preloaded model for this demo. And the XiP is homing to get ready for that first layer. Obviously, base layers always take a bit more time because they're putting extra energy to create the adhesion. And then a time lapse of the actual demo itself. Perhaps next time I should have a nice video, a music track behind this one. So removing the models, we come with a toolkit, some really sharp but useful chisels and other instruments to remove parts from the build plate, as well as do support removal. This is our washing and curing system. It's an all-in-one, as you saw when the user took the lid off. This is a very strong vortex, and we're using in this one our XClean solvent. You can also use IPA. So I'll talk more about XClean later. And then the user is installing a reflective film, and this sort of almost like transforms, if you will, into a curing station. So you kind of get a peek of the inside of that hood. It's got an interior reflective surface to keep the UV power in. She sets the time, and then parts are done. So that's a quick demo taking you through the entire workflow in a bit of a montage way. Okay, so I mentioned this all-in-one station. There's obviously, I'm showing two things here, but they're really just one thing. It's an all-in-one part washing system. And I mentioned earlier that all of our parts that all the materials we sell are validated through this post-processing system. And it's very, very small footprint on your desktop, and it's very easy to use. We'll give you a really great set of tools to work with to both remove things from the build plate, clean your build plate, clean your resin tank, and also post-process your parts. And finally, we also have an accessory here for the desktop called the XiP Air. And what we always recommend when you're printing is you print in a well-ventilated space, but it's no secret that vat polymerization does have odors and also has some chemicals. So what we've done is we've designed a typical home filtration system, but we've added 5 times the amount of activated carbon in it to trap exactly those species that people are most concerned about. So this gives you a bit of extra peace of mind at the desktop, should you choose. And then that's what the entire post-processing system looks like. On the far left of this slide, you'll see the XiP up there on a higher level. But then this is what the extra post-processing footprint would look like to keep you safe and ready to go. All right, so outside of the printing aspect, what else comes with the XiP? Well, we have a customer ecosystem we're building out. We're going to have a mobile phone app to help you manage consumables. That's coming soon. We have a storefront, we have a support site, and we also have a team of professionals, which we call our Evercare service plan, should you want extra help or extra support from us. For XiP, we have 2 levels of servicing support. We have a universal support. So this is free access to anyone, whether you've purchased a printer or not. You may have a student who downloads the free version of NextX and uses a departmental machine. That person can still access our knowledge base, access our live chat and email support. And then for teams that want additional levels of support, we have an Evercare services plan, and that gives you a dedicated set of agents, onboarding training, contact with us in any format you want, phone, video, SMS, it's fine. We'll work to whatever works best for you. And it includes a printer hot swap, and then also includes priority handling and consumable subscription. So sometimes you get into a jam, you need some resin, you don't have it, and you put an order in, but if you have Evercare plan, you can, since we're shipping out of our headquarters, we can also work through our own HQ and fulfillment to get you that, part of that consumable or material out the door as soon as possible to keep you active and going. So I think that probably is all of the printer, the background on the printer. I do want to finish up where I started around this idea of sustainability and this message that we're doing. So there were a lot of decisions that we made as we were building out the XiP, which impacted sustainability. And probably at every step of the road, we basically took the path that led towards sustainability with this product. And it makes us feel good, and it's the right thing to do. So you'll see a lot of aluminum in this machine. The enclosure, the actual consumable bottles are aluminum, and this is meant to be recycled. Aluminum is one of the most recycled materials on the planet, and so we hope that you will do the right thing. Also, because we're using high efficiency LEDs and we're basically just sipping on electrons here, we're trying to put as much of our electricity into the print process itself. So 84% of the power that we pull out of the wall plug goes actually into the act of creating your part. And there's not really a standard on that, but if there were, I'd hope to say that we'd rank pretty high on that. The membranes are replaceable and recyclable. And we've meant for this machine to be upgraded modularly. So we have made accommodations for potentially future generations of LCDs and other things in the model already. I mentioned earlier XClean. It's a safer and also a better solvent than IPA for cleaning parts, and you create a lot less waste. And then lastly, this is something we really believe in. We actually have a forest of trees that we're growing in Tanzania. And so for every XiP that is sold or put out in the world, we'll plant a new tree in the world as well. So that's some of the commitments that we have to sustainability. And while it may not be a primary decision point, we hope that it does become one for you and put a more positive light on the XiP as a potential next desktop printer for you. All right, so that's it for me. Thank you for joining. And if you want to learn more about the XiP, we have a website. Come see the website. And we are offering a promotion for now until the end of May. If you see what you like what you see and you think the XiP's for you, by all means, you can come request some samples from our website. But if you order by the end of May, we will throw in a free liter of our X Pro 410 prototyping resin from Henkel as a courtesy for taking the leap of faith and joining what we hope is going to be the next greatest desktop 3D printer without compromises. And so with that, I will take any questions.
Okay, Mike, I've been, I think you have to grant me video access again, but I've been tracking the questions that have come in. I've answered a few, but they've been coming in fast and furiously. So I can toss as many as we can get through your way here. Bear with me. So let me start at the top. Okay, so how would you, Mike, compare this printer with the latest Formlabs printer?
Okay, that's a great question. So I would say that I think we're talking about the Form 3 Plus. So the first thing is the type of print process. So the XiP is using the LCD-based, LED-based light engine process, and Formlabs is using a laser-based system to cure their layers. So you're going to get difference in terms of how fast those prints come to fruition. So that's one of the main benefits of the current DLP or mSLA, where you can create that full layer of printing. So you'll find faster printing is probably the predominant thing you're gonna see between the two.
Good. And then we've got a sort of a two-part question here that has come in from a couple of people. Can you, I think you covered it on an earlier slide, Mike, but can you comment again on the accuracy and the resolution of prints on the XiP? And then the second part is, are those printed parts isotropic? Okay.
So I can answer the second question easily. Yes, they are isotropic. That polymerization process is well known for creating isotropic parts. And in terms of the accuracy and the precision of the XiP, we haven't done a complete study yet, but what really is the feature size, which is critical, is that pixel size. So getting down to 52 microns is the smallest thing that you could achievably print or put light through. To give you an anecdote, the sample parts that we've created, we create build plates of 20 at a time. And so we measure the outer diameter of each of those parts coming off. And so over that build plate, we're seeing a deviation of plus or minus 20 microns across those 20 parts of that one dimension. So I think that's coming from the idea of you have the sub-pixel resolution you can actually achieve through the anti-aliasing. So you can get down to that level of precision. So if you start printing a part and once you work out any scale factors that are systematic, you're probably going to get down to plus or minus a pixel or plus or minus a half pixel from the residual accuracy that we can't, it's inherent to the XiP.
Yeah. Can you comment on the curing times per layer for the different resins? Now, obviously that varies, right? Depending on the resin, but maybe generally speaking, can you comment on the curing times?
Yeah, sure. So in general speaking, things that are more transparent or translucent tend to cure faster than, say, things that are darker, as well as things that have typically more functional or higher performance. Those also take typically longer to cure. So you might have one resin might take a second to perform the curing operation, and you might have another one that might take 10 seconds because maybe it's a darker material or it's got a higher performance, and so it's taking longer to create all those chemical bonds. So probably in that 1 to 10 second range is fair to say. That's part of the process because you still have to peel and recover and get ready for that next layer. So curing is one aspect of the print time, and then the other aspects are how quickly you can get your build platform back in position for that next layer.
Does the printer have internal vat heaters to maintain the resin at a consistent temperature during the print? And would it work well in a cold environment, say a not well heated area of a factory? In other words, sort of what's the optimal resin temperature?
Yeah, great question. So we recommend a certain environmental area to start with. This system does not actually have a heater in it. One of the things that we've seen is when any of these curing reactions are exothermic and they actually can generate a lot of heat. So we've been able to get through all our validations, printing for the most part at room temperature with our resins without doing any additional extra heating. So we'll keep an eye on that, and we'll see how that trend continues. But at the moment, we're able to achieve really great parts without the need for a heater.
And then taking that a step further related to resins, when changing resins, what happens with the resin in the resin tank?
Okay, so if you're changing resins, you kind of have two options. You can either use a new vat, like a fresh vat, in which case the old vat or the old material you could put into we'll have a case for you and put that on the shelf and almost kind of create like a library, a shelf library of resins. And they have a lifetime on the shelf, 30 days or more before you have to kind of think about, is that resin still valid? Or you can take the one vat you do have, and then you can basically filter that resin back into your resin cartridge, and you reuse that vat and reuse that membrane. That obviously takes a little bit more elbow grease on your part, but it's definitely a possible scenario. And our vat will have a spout on it, which will help you pour out of the vat, as well as our cartridge will come with a funnel in our accessory kit. So we do want to help you get things back out of the vat to clean appropriately and do that in a mess-free way.
We've got some post-processing questions here as well. What are, if you can comment, Mike, what are the typical wash and post-curing times that we've seen? Again, that's somewhat dependent. And then somebody also related to that says, I like the compatibility of the wash and cure station. Is the wash feature just a vortex, or is it also ultrasonic?
Great question. The wash is, I think, really amazing. It takes just a few minutes to wash. You can either do a single stage or a two stage if you prefer. Excuse me, and we're talking like less than 5 minutes. Some are 2-minute washes. It's an impeller system. There's not an ultrasound, and it does a really good job of cleaning. I'm always impressed by it. The curing, we recommend, most of our validated workflows require 2 30-minute cure sessions. So you cure on 30 minutes, and then the part rotates, but then you might need to flip it over and then change the orientation of it to get another 30 minutes of complete cure.
Good. Thank you guys for your patience. A lot of great questions here. We'll spend maybe just a couple more minutes on questions just to respect everybody's time, and then we can certainly follow up with others that we don't get to. Mike, can you comment on the average lifespan of the Everlast membrane?
Sure. Yeah, the membrane is rated, assuming there's no error or like a puncture of the membrane, they are lasting more than 50,000 layers. So if you're thinking of a 100 micron layer height, it's basically printing a tower of parts 5 meters high. And so that's what we're currently rating the membrane at.
And then a couple software questions just to confirm the plans that you went over, Mike. With the basic plan, do you need to pay for any software license? And if yes, how often in total cost?
Yeah, so the basic is free forever, and so free forever. And then the pro version is an annual license that we would deliver to you. And then it's basically almost like the old Microsoft way, where you put in the heinously long set of digits, and that unlocks the additional feature sets in the software.
Good. And then speaking of software, this question came in earlier and I was in the process of answering it before we got to the end here. What is the upper limit in terms of file size that the software can handle? So I can actually take this one because I was trying to answer it. So we've tested many files, and what we've found is files over roughly about 1.5 gig model files can sometimes have issues, obviously, during importing. But we've also seen this obviously be geometry dependent. So some files that are even around like 300 megabyte size, depending on their complexity, could take longer in terms of support generation time. So it's not only the file size that can have an impact on the software and time to process, but also the geometry and the complexity of that geometry in the model. So, so that's sort of what we're seeing today in terms of the size and having maybe any issues during importing. We're always looking and continually improving our support generation and slicer to handle increasingly complex geometries going forward. And then with that, just maybe grab one more question, Mike, and then we can close out here. Well, let's do two questions because these have come in a couple times. When will the zips be available to ship, and is financing available to purchase?
Okay, two great questions. So the zip is, if you go and order currently, it's an 8 to 12 week lead time. So our goal is to be shipping the first units mid-June to the people that placed orders initially, and we'll then fill the orders in the order in which we got them. And then the second one was financing. We don't have any online financing, like, you're a firm type of things. There maybe through Shopify, if you go online, I can't recall. If failing those, we do have some financing partners or financing brokers who we've used, who can, we'll take your details, and then we'll basically come back to you with a proposal on what financing would look like if based on your credit score, et cetera, et cetera, et cetera. I'm not in that field myself, but we can put you in touch with people who we've successfully done that with in the past.
Sounds good. I think we're a few minutes over. I think that's all the time we have today for questions. But we know the interest is high, and there's still some great questions that we will help answer. So if we didn't get around to your specific question, we've got them noted. We will follow up with you separately to address it. And like Mike mentioned, for even more information, whether it's for material specifications, for pricing, or to request a really cool free zip syringe assembly sample part, visit our website. There's a lot of information out there. Or again, don't hesitate to reach out directly to us. Mike's information is there, and consider taking advantage of that free resin promo by the end of May. So thank you all again for attending today. We will follow up with you soon with the contents of this webinar, as well as answers to any of your questions. Thank you so much.
Thank you.